Is everyone in the right place? Yeah. You want to hear about async programming? Cassandra, Akka? Who came because it was Akka? Cassandra? Who just likes async stuff? Fair. So we're going to be talking about what the merits of doing asynchronous programming for two reasons. One is for scalability. The other is if your problem actually just fits into that programming model. We're then going to look at a couple of examples. So Akka for an application, and then Cassandra as a database. Even if you have no intention of ever using Akka or using Vertex, say, which is on the other talk, or a different system other than Cassandra, you should still get something out of the talk. I'm mainly talking about the reasons for, say, scalability, which is just as applicable if you're trying to get the best throughput out of a different database system or a queuing system or a replicated cache. It doesn't really matter. So I'm not going to give you my life history, but I will tell you about why I'm talking about these topics. So from the Cassandra point of view, I've built applications with Cassandra for many years now. It's been a while since I've actually used a relational database, done Mongo, done Cassandra, etc. I am one of the contributors for Akka Persistence. So if you don't know what Akka is, hopefully you will by the end of this talk, it's essentially a way of programming to actors and sending messages between them. That's all in memory, but if you want to persist things, to persist the events that come from those messages, then use Akka Persistence. Akka doesn't come with a database, so there are plugins for it. So I work on the Akka Persistence one. And finally, one of my projects that I work on a day-to-day basis is a testing library for Cassandra. So this actually implements the same native protocol, the on-the-wire protocol as Cassandra, and it pretends to be it, which means that your application thinks it's connected to a 20-node database cluster across two data centers, when really it's connected to one fake thing. And that is actually built with Akka, so that's why I love talking about these topics. I want to understand what you want to know, though, because out of the three sections, so generally talking about async programming, talking about Akka, and talking about Cassandra, I can spend more time on any of the three. So who here has actually developed an application using Akka? Anyone? So not many. How about Cassandra? Again, not many, so it's new to everything. Who has used a servlet? Anyone use a servlet? Or a framework built on top of them, like Spring MVC or Jersey or all of these? So we're used to servlets. Now I'm going to assume that there's going to be much fewer hands go up here. How about the async servlet API? Who's done that? Who likes it? Still, yeah. It's retrofitting synchronous APIs with synchronous APIs with async APIs often has interesting results. And then the last one, before you can start to sleep and ignore me, is Netty. Who's used Netty directly? So if you're doing any programming with NIO, I definitely suggest you check out Netty. I'm actually at the point now, whereas if I pick up, say, a HTTP client or a database driver, and it doesn't use Netty under the covers, and it's Java, I'm very suspicious, because they've done some awesome work on basically having non-blocking I/O for networking. So we're going to cover reasons for going async. It is not always a good idea. So don't leave this talk thinking, I want to make everything asynchronous. That is not a good idea. We'll introduce Akka and Cassandra, and then we'll have a look at some code examples. There's a very large working example, which is very similar to applications I've developed for companies, that's on GitHub that you can go and play with, that's using Akka and Cassandra. So it's going to start off looking a little bit like this. This is a really complicated architecture diagram that I put together. And what it is it's taking data from many thousands of weather stations. So very small ones, probably running on things like Raspberry Pis, all spread around the US. The data is then ingested into a cool system, which we get paid lots of money to develop. And then it needs to persist the data. It needs to be durable. The only the hard part of this is it's going to be coming in at 50, 100,000 concurrent transactions a second. So we need to rethink how we're going to architect this application. When you start to build applications which run at this scale, so we're in the hundreds of thousands of concurrent requests a second, you often, or I've led to believe, that separating the write API and the read API is a very good idea. So rather than having the same application dealing with the actual runtime operational queries coming in, we're going to have a separate application to do that. There are some good reasons for this, and you can look at some of the literature regarding CQRS and event sourcing and things. But the reason I normally do this, if it's a high throughput and I want high availability, is the ingestion system, the thing which is writing data, often has very different SLAs, so service level agreements on things like uptime, than the read side. So in my relatively short career, I have worked on applications where it is absolutely imperative that the ingestion framework for the data never goes down. So maybe it's coming in over HTTP synchronously, and if we do not get that onto disk or we don't get it written somehow, it will never come back. So downtime in the right application means lost data. On the other side, I've worked on systems where it doesn't really matter. So the data is actually coming from some type of persisted queue or replicated commit log, something like Kafka or WebSockets or something, and you're reasonably confident that if your consumer of that data goes down, you'll be able to get it back at a later time. And again, the same for the read API. If we've got a caching system in front, it going down just means that we have stale data. It doesn't mean that perhaps our customers are going to see our system as completely down. But when you start dealing with bigger data volumes and bigger transaction rates, you're often struggling to keep up. So let's say the write system is denormalizing. We forget about normal form for a while, and we store it, say, 3 different ways. So we're almost like joining on ingest rather than joining on read. Because joining works very well when you've got a reasonable dataset size that fits in memory. So if it's still in the 100 gigabytes, in the hundreds of gigabytes, joining's fine. As soon as you get into the terabytes spread across many different computers, you can't join. Or you can, but it's extremely slow. So what I've worked on a lot recently is where we've got this vast quantity of data, we've saved it different ways so that we can read it a number of ways, but then we're going to run some type of batch processing on it. Now, traditionally in my history, that has involved taking all of the data, sticking it into HDFS, running MapReduce on it, then putting it back into my operational database so the consumer can then come along and read it. Though over the last 3 years or so, I've moved to being able to do batch analytics directly on my operational database. So taking that data, running something like Spark, doesn't really matter what the technology is, and then doing things like you would be able to do like natively inside a relational database, building up reports, doing group bys and aggregates and things. But because we're dealing with larger data set sizes, we're going to use something like Spark, which is just, if you've been to the talk earlier today, you know exactly what it is. But it's a good way of doing distributed computation across a large data set. And it's really easy to do that on data inside Cassandra. Last but not least, though, is people get very impatient. And you then eventually decide, I don't want to wait for my batch job to complete. I want to do something like stream processing. Now, if you've never done stream processing with something like Apache Storm or Spark Streaming, don't think it's complicated. It's really not. You probably have done lots of stream processing. If any time inside your application, you've kept a count of how many web page hits, etc. have come in. That's stream processing. You're just not using a fancy framework. So you can get away with doing things while you're ingesting your data, populating other fields and counters, etc. without a framework. It gets useful to use a framework like something like Spark Streaming when you're spending more time developing the functionality to say, hey, I want the daily aggregate rainfall for the last 5 minutes, but I want it as a rolling window every 5 seconds. You'll spend more time coding up that rolling window than you will your actual business logic. So that's when it's useful to bring in something like a stream processing. Now, we can't talk about all that, but if you want to talk about all that, then just grab me afterward. We're going to talk about 2 little parts of this diagram. We're going to talk about consuming the data asynchronously on the consumption path, and then we're going to simplify it and look at the ingestion path and how we can get many tens of thousands of transactions a second, durable writes, out of the systems that we're building. And for me, it started with I'm going to start it with a little story. So, I was working at a company, it was called Sky Television. They provide most of the television to most people in the United Kingdom. And we were doing online television, and we were trying to keep track of everything all of our customers ever did. And we did some calculations based off the existing data. That was going to be about 40,000 concurrent requests a second. No, sorry, just 40,000 concurrent requests. Now, we were using an older version of Cloud Foundry. And if you haven't come across Cloud Foundry, it's just a platform as a service. You basically give Cloud Foundry all of your servers, and then you can throw like WAR files at it, or executable jars, or Docker containers, and it will just run it for you. if you throw a Java application at it, say a WAR file, what it actually does is it spins up a Tomcat inside it. If you're no modern Cloud Foundry, it may have changed. This was Cloud Foundry 1. But the default configuration for Tomcat is 200 threads. So the the thread pool it's using to accept your connections from the operating system is 200 threads. So if we want to handle 40,000 concurrent requests, and each of these Tomcats that were spun up for our application could handle 200 concurrent requests, how many instances did we need to ask for? How many running Tomcats did we need to service 40,000 concurrent requests? 200. And we had a pre-prod environment that matched prod exactly. And this was 400. Do you know how much it costs to run 400 instances in Amazon or in AWS per year? It's a lot of money. It's in the hundreds of thousands of dollars. When we switch this to a 2-server asynchronous model, we're literally talking about saving hundreds of thousands of dollars. This isn't always the case. The reason this was the case is what that request involved was doing some parsing, doing very few things on the CPU, and then writing it to a database. So it was mainly I/O. All of those 40,000 threads would just be blocked on I/O 95% of the time. You don't get quite the benefits if you're a CPU-intensive process. But there was a problem with this, and we don't really want to do it. And it pretty much, lots of developers and lots of people I talk to, myself included, we love to see the world in request and response, both at an application level, so a HTTP request, and at a programming level, so say a method invocation. So we're used to this. It's how HTTP is built. Before we got Keep Alive, we even established an entire new TCP connection for every single request. This is fine if you're doing a few hundred transactions a second. We can't do it when we want 40,000 concurrent requests. No one is going to pay for those AWS instances for us. Admittedly, I don't build many front-end applications. I'm a back-end brat. I would rather learn more about distributed databases than learn JavaScript, unfortunately. So I'm going to turn that into another little server. But many of the interactions we're going to have to build the application I was discussing, they are not request response. So the ingestion is a bit like fire and forget. The reading, the consumption side, you do not want your other applications to have to poll you for information. This is not good. It's a waste of resources. You know, it's more like publish subscribe. So when I want to read, hey, is it rainy in California, which I'm guessing it never is because it's a desert, it comes in and then it just constantly gets updated. Whether this is over a TCP protocol or over WebSockets, don't really care. But it's not synchronous, and it's not a request-response style interaction. It can even get more complicated than that. Requests in back-end systems, it might go into one system, you might get a couple of responses, and it might involve having like some form of multicast. So we get to send it to a few other servers. So we need to just get out of the way of thinking about everything as a synchronous request-response. But it's about time you actually learned something about Akka and Cassandra, because I've just been bubbling until then. So we've had lunch, so you shouldn't be hungry. So this shouldn't make you think, ooh, I'm going to leave and go to lunch early. But we're going to build a sandwich, and the bottom is going to be Cassandra. And I'll describe when it's a good idea to use Cassandra, and the many cases when it's not a good idea, and you should stick to the technologies you know, e.g. Oracle or Postgres, etc. On the front, because this is a runnable application that you can go and play with if you want, it is WebSockets, but I'm not going to talk about WebSockets. I will very, very briefly. And I want to talk about the importance of making sure that that middle slice is asynchronous. There is no point doing asynchronous programming if you stop halfway through and then block a thread, because that thing will then require a thread pool of 40,000 threads. There's also no point using, unless you just prefer the programming model, of having an asynchronous access to an inherently synchronous technology. And I'll talk about that in the future, because Cassandra did used to be a more synchronous technology. So let's learn a bit about Cassandra. So Cassandra is a self-selecting technology. For those of you who don't know, it is a distributed database. It is used a lot. So normally people pick it because they're either at higher scale or they have availability requirements. So if single servers go down, like the master of your traditional database, you can't handle any downtime. It is very good at storing ordered data. So it's heavily, I'm from London, I do consulting on Cassandra, I spend most of my time at banks. So they use a lot of Cassandra because they do a lot of immutable time series data modeling, which means, like stock prices ticking or your bank balance, which is actually made up of transactions. If you actually Googled who uses Cassandra, you would find that Apple are the biggest user. I was at I was in San Francisco last weekend, and they announced that they're now up to 100,000 nodes of Cassandra in production, which is a bit crazy. I don't suspect that your application requires 100,000 nodes of Cassandra. But one of the great things about it is you can deploy it across multiple data centers in an active-active fashion. By that, I mean we can access the same data from multiple data centers and write it. You have to worry about conflict resolution, but it works that way by default. So it's heavily used in any industry where they need to be, distributed across the world so you're close to your customer. Again, finance is a big one there. They're going to need a New York and a London and somewhere in Asia. And things like the multiplayer, like matchmaking services by gaming. That's another thing where they need local data centers for people. So you don't like latency when you play games. So yeah, the reason for that is, I'm not going to go into too much detail, but you can quiz me after, is when you do data modeling inside Cassandra, you actually decide the order it's stored on disk. That's one of the things. This is because you can then do really quick querying of like time ranges. It doesn't have to be based on time. It could be based on, say, an integer or, say, based on characters, but it's mainly time series. But not many people think, ooh, I've got some time series data. I really want to you really want to model that in Cassandra rather than something else. It's normally for non-functional requirements. So there's a trade-off with a database like Cassandra. You're going to lose your ACID transaction, and you're not getting it back. You have to deal with eventual consistency. And as an application developer, you have to trade off. When do I want the latest response, or when do I want to suffer some latency? If there are so many nodes down, I can't have as high a consistency on write. And we'll see how some of that works. It came about from a couple of papers, one from Google and one from Amazon. And we'll go through them briefly. So the distributed architecture, which I'm going to describe, which essentially means that Cassandra replicates data across many servers and allows you to go to any server to get or write your data, that comes from an awesome paper called Dynamo. I suggest you go and read it. You will learn things about databases and trade-offs from that paper. It describes how they built their shopping cart service. They discovered that if you can't add things to your basket for Amazon, you eventually lose some money, or they lose some money, and it's not good. They would rather you accidentally buy 2 Kindles rather than 1 because of a consistency issue than buy nothing at all. They'll happily give you a refund and say sorry and make it up for the small case. That described a key value store. So key value store is, you're very limited into how you can model data. So it's a blob. Literally, Dynamo is a blob key to a blob, value. That is not what Cassandra is. It's what's often referred to as a column family store or a wide row. That's where you get to choose how Cassandra orders things on disk so you can access it very well. So for a particular key inside Cassandra, something we call the partition key, you can store hundreds of megabytes of data ordered the way you want. And as long as you do queries within that partition, they'll be quick. And you can go to one node to go and get them, regardless of how big your cluster is. It could be 1,000 nodes, it could be 1 node. One fantastic thing, and the reason I actually got to Cassandra in my development career, was multi-data center. So there's 2 reasons to go into multi-data center. One is to get local with your customers. So you've got data locality. The other is fault tolerance. I have been paid to develop software for 8 years now. And in that time, I have had 2 full data center outages. One was when a hurricane hit New York, good old Hurricane Sandy, and I was working at an investment bank. And the other was when a network configuration issue meant our data center was fine. No one could get there, though. So when you're trying to build always-on software, and when you're trying to be, say, Netflix or Amazon, you're not deploying your services to a single data center. And there aren't many databases that support that pretty well. That whole Spark thing I showed you about doing batch jobs, it is a terrible idea to do batch jobs on your operational database. You probably thought I was a bit of an idiot when I said, yeah, I want to run my batch jobs on top of my operational database. Who here has done a query inside, say, their database and slowed down production? Anyone? Don't worry, it's dark, it's fine. We've done it. Often they're big delete statements because we want to get rid of old data, but we've all done it. The Cassandra allowing you to do multi-data center, you can actually lie to it. You can tell it a little fib. And even though you're in one data center, you can pretend it's in 2, and you can send your batch jobs to one and your customers to the other. So the worst case scenario, you can destroy your analytics framework, not your operational database. And that's why it works. That's why you can actually run Spark on top of it without killing it. Because Spark is the easiest way to kill a Cassandra cluster. It will read and write at crazy volumes. So how is the data distributed? You know, we've got all these servers, and there are people running multi-thousand node clusters. So sometimes it's a lot of servers. There are also people running 3 node clusters. If you're running a 1 node cluster, you probably should have picked Postgres. So we store regular data. You're probably quite familiar, tabular data inside Cassandra. You can think of it, though, as like a map of maps. So you've got a partition key. This is this guy. This can be 1 column, it can be 6 columns. But you have to tell it that. You have to know your data. You tell Cassandra, I would like to partition on this particular value. So in this example, it's name. It's Jim or Carol or Johnny or Susie. And what Cassandra will do, every single row inside Cassandra, which has the same partition key, will live on the same node. So it can't be too much, because it's got to fit on a single computer, but you don't want it to be too small, because you want to keep your queries in there. So regardless of the size of your Cassandra cluster, you can go to a single node and get the data. How Cassandra does that, and this is from the Dynamo paper, is consistent hashing. So what Cassandra does is it hashes that value that you've told it to, and that gives a number. The real value of that number is a 128-bit value. Well, there's different partitioners, but it can be a 128-bit value, which is a really big number which I have no way of saying. So I'm going to pretend when describing this that it actually hashes between 0 and 999. So we're going to pretend that murmur3, and this is a lie, this is not what the murmur3 hash function will do, will actually hash the bytes of Jim to 350, the bytes of Carol to 998. Cassandra then assigns token ranges of this hash function to different nodes. So node A here owns all of the data which partition key hashed to 0 to 249. Node B owns all of the data between 249 and 499. 250 and 499, sorry. You often see Dynamo-based databases, so Ryak is another one, Cassandra is one, as rings. And it's because these values are used to arrange all of the nodes in a ring. So we can see that all the data for, in here is owned by node B. And you can work this out deterministically. If you can go to any single Cassandra node and it knows where to route your request. But it doesn't often have to do that because the drivers do it. The driver gets information from the Cassandra cluster about all of the nodes and where they live in the ring, and then it directs the request directly to the node which owns your data, both on reads and writes. Because we can work this out. It can basically work this out in its head, or in memory, because it's a computer, it's not a person. And you can see because Johnny hashes to 50, it's going to be on node A. But this isn't the end of it. If this was the end of it, what would happen to poor Johnny if node A went down? He would cease to exist. We'd be back in the problems of a single server database when that server goes down. So this is not the end of the story. The next thing Cassandra does is it replicates your data. All of this are reasons why it can handle so many transactions a second, because even when you're reading data, it can actually go to many nodes in the cluster because we replicate it. Now, rather than tell you exactly how Cassandra does that, I want you to tell me. So imagine you've got a normal database. It's a single server. And you took a backup of that database. Where would you put it? Would you put it on the same computer? Anyone? Anyone in ops? You probably shouldn't put it on the same computer, even if it's a different hard drive. This is a bad idea. Data centers are arranged into racks. Groups of servers which have they have like their own switch. They possibly have the same power supply. Would you put your database backup on the same rack within your data center? Probably not. They often go down together. When someone trips over that network cable, they can quite easily take out an entire rack. Same with power supply. So you're probably going to put it on different racks within a different rack on your data center. Now, assuming you're a pessimist like me and you assume that there's going to be another hurricane or tornado that hits your data center, or an ops guy is going to come in and pull something out, would you put that backup in the same data center? Maybe. You might only have one data center. Maybe now in Amazon, pretty much anyone can, deploy things across multiple data centers. But if you're building your own, it takes some time to build a data center. So that's pretty much what Cassandra does. Every node inside a Cassandra cluster is aware of what rack it's running on. You have to tell it, and what data center it's in. And in that way, it uses the network topology to be resilient to both failures and network partitions. So what does it do? So every Cassandra node knows which rack and data center it's in. There are many ways to tell it. You can literally just say, hey, node A, you're in rack blah, data center blah. Or if you're running in something like Amazon, it can just work it out itself. It can hit the metadata service and it can say, I'm going to treat an availability zone as a rack and a region as a data center. Job done. Then when you write your data, we get the first replica by hashing, but then it walks around the ring and it selects the additional replicas to make sure that they're not on the same rack. Unfortunately, and there's a feature open for this, and we'll see whether we can get to it at some point, Cassandra can't invent racks. It can't create new infrastructure for you. So if you actually ask for a higher replication factor, because that's something you decide, then there are racks in the data center, you will end up with multiple copies on the same rack. So there's no magic involved there. All of this means that the way your data is distributed in Cassandra is actually quite complicated. It's spread all over the place. A very common setup is to run in 2 data centers and have at least 3 racks in each data center. And so your data is actually spread across 6 independent racks. So you can handle 5 of them going down. So like 5, 6 in that respect of your database, of your servers going down without actually losing any data, which makes writing slightly more complicated. So let's say that you actually want to write some data inside Cassandra. What the driver does is it does the hash, it goes to a node which owns the data. That then works out the algorithm, and it'll work out everywhere in the cluster it needs to go. However, you as a developer have a decision to make. This is the trade-off. This is the thing which makes it harder to use Cassandra than your traditional, say, MySQL or Oracle. Because you have to pick a consistency. And what you're essentially doing there is asking on write how many nodes you want to wait for. So we've got, let's say we're doing 2 data centers, 3 replicas in each, 6 total replicas. You get to pick as a developer how many it gets to. It's going to get to them all, but how many it gets to before you go back and say, everything is great, my data is written. So if we do consistency level 1, that means that we can come back right away. We're already done. We're saved to 1 node. We're happy. However, what the coordinator will do, that node that you connected to, it will replicate it out asynchronously into the local data center. It won't copy it 3 times over to the other data center because it's assuming that that network link is either expensive or slow. We could be either side of the Atlantic. So it copies it over once, and then that guy copies it over to 2 other nodes. And that's pretty much it. That's a write, but on a read, rather than deciding how many nodes to wait for acknowledgements for, you actually decide how many nodes to consult. So if you say, I want to talk to at least 2 nodes, you're going to get, the latest data from those 2 nodes. You have to tune this, though, because given that data is replicated, say, 6 times in a Cassandra cluster, 3 in each data center, then every time you do a query, and you can set up defaults, don't worry, you have to specify it. So there is one called all. What do you think all means? Every node. So we don't normally do that, because availability then is terrible. Because as soon as one node is down, Cassandra will just say, I can't do that. I can't get to all of them. Quorum is a popular one. So rather than actually worrying about how many replicas are inside, however's configured your Cassandra cluster, let's not worry about how many they put. Let's just make sure I get to a majority of them. So if we've got 6 replicas, it will get to 4 before coming back. But if we think about the topology from the last example, that's 6 total replicas, and we want to get to 4 of them. But one of those is on the other side of the Atlantic. Now, due to physics, we can't get there that quickly. So you can actually decide to just talk to the local data center. And instead of getting a quorum across all 6 replicas, we're only going to get a quorum in our local data center. Unsurprisingly, that's called local quorum. So we'll go to at least 2 nodes out of the 3 in the local data center before going back to the client. And then you have the most popular, even though it's a little bit scary if you're used to working with a relational database, of 1. So that's where you want the lowest possible latency, the fewest network hops to go and talk to other people, other nodes in the cluster. You just want to go really quickly. If that scares you, if that makes you think, I never want to develop an application against Cassandra, I suggest you go and watch this talk from Netflix. They use Cassandra for everything. And they are across 7 different data centers. And they have a talk there on how they write at consistency level 1, but then record how long it takes to get to each of the other data centers. So their little thing, tagline is, it's eventual consistency, but it's not hopeful because we continuously measure how long it's taking. So before we start talking about, forget about Cassandra now, that's all you need to know for the rest of the talk. Before we start jumping into Akka, etc., I want to get I've got another quiz for you. So you're going to have to wake up again. So I'll give you a moment. You're all awake. Who here has used or programmed against an executor? Executors in Java, executor services. Yep. Who's done future programming? Java's future is terrible, but we have to use it sometime. What about the listenable future from Guava? Or another listenable future from lots of other libraries? This is like a future in Java, apart from the fact that you can set a callback on it. So for those of you who haven't come across futures, it essentially means I'm going to have this value. It could be from a database, it could be from the file system, it could be from a long computation, but it's not there yet. It'll be there sometime in the future. And pretty much the only thing you can do in Java future is call get, which then blocks. Doesn't seem very useful to me. A listenable future, which is an extension by Google, is one which allows you to add a callback. So you can say when that value is actually there, say it's come back from a database, please execute this code. But if you're not too careful, you end up with something that looks a lot like Node.js, and you end up with a lot of things that are lots of callbacks that become ugly. So to go even more hipster, who's used an observable? So RxJava, reactive streams. There'll be no observables, I was just curious. And if you're hip with Java 8, people say the greatest thing about Java 8 are lambdas. I disagree. I think the best thing about Java 8 is the completable feature. Has anyone used one of these yet? It's like a feature, but you can actually do stuff with it. It is good, so we like these. The DataStax Java driver for Cassandra, don't worry, that's free and open source, it returns a listenable feature. So we can deal with it asynchronously. What this allows us to do is execute thousands of queries against Cassandra and then put callbacks on to say, when they're all done, let me know. And we're going to do this on the right path. And there's something very important to notice. So you can have an asynchronous framework like Akka. You can have an asynchronous client, say like an asynchronous HTTP client. But it doesn't matter if your server, the thing you're courting to, the database, etc., doesn't allow you to interact with it asynchronously. And it's a lot to do with something which often is called request pipelining. So the way Cassandra used to work, and the reason I'm going to tell you this is I want you to evaluate the technology you're using at the moment, is it used to open a TCP connection, and it used to make a request and get a response. Make a request and get a response. So you could only have one concurrent request on a particular TCP connection. This is not good. This is why HTTP doesn't scale. If you're ever wondering why Chrome uses so much memory and makes so many connections to all the websites you are, it's because it makes 8 connections per domain, so it can do 8 concurrent requests. This is so it can actually get some concurrency, because it can't do it over a single connection. And this is bad, because connections use resources on the operating system inside your application. And if essentially most of the time the connection isn't being used, it's just waiting for you to make the next request, or it's waiting for the server to send a response. So this is actually how Cassandra works. So from a single TCP connection, you can actually execute 32,000 concurrent queries over it with a single TCP connection. If you haven't come across HTTP 2 yet, I could use these exact same diagrams to describe HTTP now, HTTP 2. It again allows you to do concurrent requests that can even overtake each other over across the same connection. So this is good. But if we don't make use of it, if we don't actually use it inside our application, then we're being lazy. And Cassandra, the drivers actually do have a synchronous interface as well. You can just block. And all they really do is call the asynchronous interface and then call get, which is the method which blocks on a feature. And that's basically us being lazy. So we're not actually utilizing it. We're limiting ourselves to however many threads we have inside our application for concurrent requests. So if we're going to build an application which, has something like WebSockets on the top, Cassandra on the bottom, we need to make sure we're not being the lazy panda, but we're being the happy panda, right? So let's see that in action. So we're not really going to talk about WebSockets. I'll do the 1-minute overview of why we are. We're going to talk about how we would develop a consumer that could react asynchronously to events. But I'll do one slide on WebSockets. So the reason for them is essentially TCP and HTTP at the moment is synchronous. And it's going to break us if we don't have our client being asynchronous as well. And we do hacks on top of it to actually make it seem less synchronous. We do long polling and we do short polling. But WebSockets actually allow us to send data both ways and use a connection for multiple things. As I said before, HTTP 2 is going to help a lot. So we're going to be able to do many of the things that we can do with Cassandra over HTTP in the future. But we're not. There was no WebSockets in the talk, so let's move directly to the bit in the middle. Let's talk about Akka. So we know why we want to be async, but let's solidify it. This is my description of what you're doing if you use synchronous programming for high scalability applications. You're using Tomcat. We all use Tomcat? Yep, or a container which basically has a thread per request. That comes in and it does some stuffs. Like most CPUs in the world, it's probably just parsing JSON. It used to spend all of its time parsing XML, now it does JSON. Or doing Hadoop MapReduce jobs. I think that's what most CPUs in the world are doing. We call into our database driver, and then we block. So the top thread, our container thread that Tomcat has given us, we're doing absolutely nothing with. And do you know how much memory a thread uses in Java? Like just how much heap memory is it's going to use up. Any guesses? 1 kilobyte. Does anyone think 1 kilobyte? Does anyone think 1 gigabyte? Somewhere in the middle. So it's actually about 1 megabyte. You're going to use about 512 kilobytes for your stack, and then it has areas to actually allocate into. So if we want to do 40,000 concurrent requests and we want to use a thread per request, we're using about 40 gigabytes of RAM. This is why it was so expensive inside AWS. So we're not going to do that. And if we do that, this isn't actually how the data the Cassandra driver works, because that implies that it's blocking as well inside when it's calling out of I/O. But there's one question: if you're going to do this and you need to deploy more than one version of your application. Now, you could have been like me because I wanted 200 instances inside AWS. But as soon as you get to 2 instances, you need to reevaluate whether this is a good idea, because this is bad. We're using up that thread, we're using up that memory, we're not doing anything with it. It's just sitting parked inside the operating system. And we shouldn't do that because it's not free. It's using up resources. And this is exceptionally important when we're dealing with any system. It doesn't matter if it's Cassandra that can handle many concurrent requests. It could be a cache, it could be your database, it could be a queuing system. So you've got to start to think about it, because otherwise we're just letting it hijack our thread and bad things are happening. So Cassandra itself uses Netty inside the driver and the server side. So it is asynchronous on both sides. It's what allows it to run many concurrent requests across the same TCP connection. So what are we going to put in the middle? Well, we're going to put Akka. And basically because a thread per request absolutely sucks. I don't really care whether you use Akka. There are actually Java frameworks for doing similar things. I'm going to show Scala, so I apologize, because Akka in Java is very ugly. We could be using something like Ratpack. This is an asynchronous web framework for Java. Or you could be using the async servlet API, and things like Spring now have wrappers on top of that, so you get a slightly nicer programming API. But I don't think it's as nice as this, but that's up to you. It's personal preference. If you haven't come across Akka-based programming before, which Akka is an example of, it's essentially saying, rather than making synchronous method calls, which is what we're used to, right? We're doing object.get. That blocks. If that thing takes a microsecond, all is well in the world. If that thing takes 20 seconds because it's waiting to come back from disk or a database, etc., this is what we're trying to avoid. So Akka-based programming basically says, I've got some classes, I've got some actors, I'm going to send messages between them, and they're going to be asynchronous. If you want to see what that looks like, it's a bit like this. So these are 2 actors, and this is what the Java one would be like, except it would be bigger. So essentially, we can receive a message. Now, the reason it looks so ugly in Java is because it doesn't have pattern matching. If you haven't seen Scala before, this receive method, and this isn't typed, by the way, so you can receive any type of message. If it receives a message, which is of the string go, then it can send a message to another actor called server, and it can send a message called ping. But this does not happen on the same stack, on the same thread. This will happen asynchronously. When it receives a pong message, it just turns itself off. On the server side, so let's have a look at this one, all it does is it can only accept a ping message, and then it sends back a pong. Akka 2.4, which was released a couple of days ago, actually does typed Akkas. So you can say, I am actually only going to receive messages of this particular type. At the moment, you have to deal with the fact that you can receive any type of message. And you can put a catch-all at the end saying, I don't recognize this message, please stop sending me them, etc. Under the covers is this. So essentially, each actor has some form of queue. They call it a mailbox. So it goes in there, and then on a different thread, it will be received, and then it will be processed. There are some really cool properties of Akka, though, and it's particularly Akka on the JVM. The first one is, it handles everything to do with the Java memory model for you. So when you receive that message, you will definitely be able to see it. So you don't need to worry about visibility concerns. The other thing it does is the receive method. That only is called one at a time. So you can actually have mutable state and not worry about synchronization and volatile variables, etc. Which is pretty good unless you want to spend your evenings reading this. Which is if you do a lot of thread-based programming in Java, you inevitably have to understand pretty much everything out of the Java memory model. Another cool thing you can do is each actor, because it's not a thread, it hasn't got that megabyte associated with it, is you can have millions of them per gigabyte. So what you can actually do for a particular query to a database, you could spin up an actor, and then you can monitor them. So its parent, whoever creates it, is looking after it, but also you can just look after a set of actors. So inside the application, what it actually does is it spins off like 1,000 queries, and then it has another actor which monitors them. And this basically is, what we do is we watch them all, and then we get told if he terminates. Now, the reason he would terminate is if, say, we got an exception. We couldn't connect to the database or something like that. And there's another interesting thought experiment I've got for you. So when I first moved to London, I went and worked for banks, and I got given this interview question. So you didn't think you were going to get interviewed in this. So you've got to solve this problem. You have to process all the trades off a queue, right? You have to process them really quickly, and you've got a 64-core machine, so you have to use all of the cores. So there's going to be some threads involved in this. The order doesn't matter unless they're for the same stock. So say Google. So you can't reorder them, and you can't concurrently process things for the same stock. Make it so. How would we do it in Java with just, say, Java util concurrent? Well, you'd spend a lot of time designing this, right? Say you're taking it off a queue, Kafka, WebSocket, you probably eventually realize that that needs to be a single thread. Because if you call any of their libraries, there'll be a lock in there, and if you use multiple, it will actually go slower. So you'll probably have one thread which will then take it off and then put it onto a concurrent hash map, and then that might have, say, stock ID to queue. This could be a blocking queue, maybe it's not, but it would have to be thread safe. Then you'd have lots and lots of threads, say as many as you've got cores, maybe 2 times cores, consuming the messages from those queues, right? But then you need to make sure that no more than one thread consumes messages from the same queue. So you need some kind of semaphore or mutex or something. What you haven't yet discussed when answering this interview question is what the processing for a trade is. Nothing, you haven't done it. You're re-implementing the same pattern which is implemented by every single bank and every single application, but they keep on redoing it. Whereas doing it with actors is actually really hard. And the reason we can't just assign a thread for each of these is a similar reason why we can't assign a thread per request if we're having a high throughput web server. Because each of them uses up a megabyte, and if we've got a million different symbols, we can't then use a thread per symbol. So how do we do it with actors? Well, it's embarrassingly simple. You basically have one actor which takes messages off the queue. Job done. He then sends it, and you have an actor per symbol. Remember, this is a very lightweight thing. We can have millions of these. If we've got 10 gigabytes of RAM, we could support tens of millions of different symbols. And then we just send a message to the right actor, and you're done. This would literally be maybe a page of code, compared to having to worry about all of the synchronization issues that if you did it directly with actual threads. Then you get to go home, and you feel like a bit like a hero. This is where, even if you didn't need to scale, I think this type of programming is more applicable. The other time it's more applicable is when doing networking. So my testing framework for Cassandra is essentially a big networking application. It pretends to be a database. And if you deal with NIO or you deal with IO in Java, so the synchronous side, it's not the nicest API. Where if you deal it with Akka or with Netty, you just say, when some bytes come on the wire, just send me this message, please. That'll be fine. And then you don't need to worry about sleeping and blocking, etc. You just get sent messages, whenever things come over the wire, which is such a nice programming API. This was probably the first actor I ever wrote. But it's time to put it all together, and we're going to do a better job than Humpty Dumpty. So let's just have a look at some code which brings together, you will see some WebSockets, but not much, Akka and Cassandra. So it's actually using Play. So Play is a web framework which is built on top of Akka. And you can actually do HTTP and WebSockets directly with Akka now. At the time when I built this, you could, but it was very experimental. And I don't use experimental Scala things. It's experimental as it is. Okay, so we just don't. So I didn't use that. Play has a bit like a routing file. Imagine this to be your Spring MVC controller or something, except it's not actually a Scala or Java file. You're basically saying, hopefully it's kind of explains itself. When someone calls /, go to this method. So it's the web controller class, and you call the method index. Similar for station, except we're going to a stations method. And then the last one is a funny one, because this is actually the stream method stream message is going to send it directly to an actor. You can do synchronous programming with Play, though it's not necessarily a good idea. They are completely non-blocking under the covers. If you're doing things which are just going to need CPU time, you just do something like this. You return an action, and it says, I'm going to redirect it to this page. This is very simple. What you're probably going to do more likely, though, is return something asynchronous. So here what we do is this syntax here, the dashboard API, this is a way to send a message to an actor and get a response. But this isn't a method call. This isn't a synchronous method call. So we get a future back, because this is going to happen whenever that actor decides to send us a message back. Because at the moment Akka is untyped, we then basically, this is a fancy way of doing a cast. We map it to a sequence of weather stations. And then what we do is we turn the weather stations into a JSON object. This is just a JSON library for Scala, and it's an OK. So that's an OK HTTP status. So nothing exciting there. So the only difference there is we actually get to return a future, and play is not using up that thread. So we return the future to play. It then uses the thread to do other requests. Whenever the future is complete, it sends the response back to our application. Let's start seeing how we'd interact with Cassandra. So the Cassandra code in here is actually the Java API. So this will be, apart from the left-hand side where you see funky things like val, this would look the same in Java. So we can prepare statements inside Cassandra, just like you can, say, in a relational database. When we come to execute them, we always want to use execute async. There is an execute, but that's just going to block on a feature under the covers. Now, because I'm actually doing this inside Scala, what I need to do is convert the Guava listenable feature into a Scala feature. And I won't show you that code, but it's on Stack Overflow. You can go and find it. Once we've done that, we then take all of the rows, because this isn't going to turn many rows from Cassandra, and we're going to map them. And that just maps them into our object, our weather station object. That's not very exciting. That's just taking things out of what looks like a JDBC, like a result object and a row object, and sticking it inside a class inside Scala. But this isn't blocking anything. It's setting it all up, so when Cassandra comes back to us, we'll execute this. And then when that gets executed, it will complete the future, which play will then execute back to us. So because we're spending most of our time blocked on I/O, as in waiting for a response from a database, we're not using up a thread per request. So this application will handle many more concurrent requests than the equivalent Tomcat that does synchronous stuff. WebSockets are equally as cool. So when someone connects to you via a WebSocket and sends you a message, you can actually have an actor be responsible for responding. And it looks a bit like this. Don't worry about the syntax. Just know that this request contains all of the information. This is who we respond to. We can respond whenever you like. We're not going to block waiting for this to come back. If we actually look at the actor implementation, I'm not going to show you the bit of code which does something, but what it does here is it schedules something to happen every 5 seconds, and then it sends a message to itself. So what that means is every 5 seconds, without blocking a thread, it's going to receive one of these messages called a weather update, and then do something about it. What it does actually is query Cassandra, get there, and send it to it. So nothing particularly exciting there. But you can do what you want, and you're not using up a thread in the meantime. So we need to end now. So essentially, I think this type of programming is very, very useful when you need to haul a lot of requests per second. If you're just doing 50 transactions a second, you do not need to be asynchronous and learn a new way of programming and learn a bunch of new APIs. This is actually this is London. This is the garbage collection which comes down the river through London. If it only wanted to take one garbage container, you would not need to invent some kind of pull boat and put a big tug behind it. You could do it synchronously. You could just shove it on the boat and off you would go. But when we actually need to get the most out of our servers, and we've got lots of concurrent requests, etc., then you need to use different tools. And we should be aware of the tools and we should use them when we can. And that's the summary. So don't suddenly go asynchronous. Remember, look for the scenarios where it's going to be useful. So that's either when the programming model is actually useful. So we think of the trades example. That is really hard to do in a synchronous manner. Or if you need scalability. And always understand the difference between scalability and performance. So scalability is about being able to utilize the servers and scale across many servers and increase your throughput. You don't get better latency by going async. It still takes the same amount of time. Just all of those periods that you were previously blocked, you now give the thread back to your application to do something else with. And if there's time for questions, I will do my very best to answer them. If not, just come and grab me. And thank you very much for listening.